my pleasure to introduce Aaron Bertram, who's going to tell us about some applications of Bridgeland stability conditions. So take it away.
Let me first, as the final speaker, thank the organizers for a lovely conference. So I'd like to thank you very much.
Thank you.
The only drawback being, as lots of others have mentioned, that it's not nearing 8 o'clock in Buenos Aires, so we can have a drink together afterwards. So I guess we can have a drink, but not together. Anyway, I'd like to also thank the audience for hanging in there. I know it's like approaching 8 o'clock, which is way past dinner time in Utah, but anyway, I wanted to talk about, to be kind of gentle with you all and just talk about some eclectic collection of applications of Bridgeland stability conditions. There have been several mentioned already in various talks that I'll mention in this talk, but I mean, one of the themes is that, I mean, this subject, I got kind of excited about this subject more than a decade ago, and it just seems to keep acquiring momentum. So it's sort of the mainstream approach to Bridgeland stability conditions, the sort of the questions, but then the questions that come out of considerations of moduli seem to be sort of quite interesting and getting more interesting as time progresses. So it's an exciting subject. So let me start by just some notation. I'm going to let X be a smooth projective variety over the complex numbers, dimension D. Co-X is the abelian category of coherent sheaves on X. Dx is the bounded derived category, which will be sort of the main player in the game. K of X is the Grothendieck group of vector bundles, modulo equivalents. Gamma is I'm gonna sort of wipe out all the continuity in the K group of X and just consider its image under the Chern character. Sort of think of it as gamma is some free abelian group that's a subgroup of the Q cohomology of X. So for example, if X is a Riemann surface, then gamma of X is just Z plus Z being the rank and the degree of the vector bundle. But if X is a algebraic surface, then the gamma of X is the rank plus the Néron-Severi class of a bundle, of a line bundle plus Z. So this is a lattice and its rank is the Picard number of the surface plus 2. So if S is a algebraic surface, this is at least rank 3 and often higher rank. Okay, so Gesiger stability was gone over very well in Victoria Hoskins' talk. So I refer you to that talk for any details about this. But in Gesiger stability, you fix an ample line bundle, and then the idea is that with respect to this ample line bundle, there's sort of a canonical moduli of stable coherent sheaves with any given Chern class. So just really quickly, Victoria did this very thoroughly. You let the slope of a coherent sheaf be a monic polynomial, which is just the Hilbert polynomial divided by the leading coefficient, or maybe not quite the leading coefficient, up to a multiple. I mean, up to a single multiple. It's just the scaled Hilbert polynomial. And then this is the polynomial slope of a coherent sheaf that we compare sheaves with subsheaves. When F is a torsion-free sheaf, which was the situation the setting in which Gesiger originally sort of talked about these moduli spaces, constructed these moduli spaces. This is just the Mumford slope to first order, which is first Chern class over the rank. And then in case of sort of tie breaks, then higher Turing classes of the coherent sheaf come into play. If F is a torsion sheaf, then it's something analogous. Anyway, the big theorem is that when you define a stable coherent sheaf to be, as usual, one such that all the subsheaves have smaller slope, then and you define families of coherent sheaves as usual as sort of flat families. Then stability is an open condition. You have good moduli, and in fact, you have projective moduli, which are constructed, again in Victoria's talk, by geometric invariant theory. Technically, you have projective moduli for semi-stable equivalence classes of coherent sheaves. So, yeah, I won't go into the. If either you know it or you don't. If you don't, you can look it up. But the idea is that, yeah. Well, I'll say a little bit about semi-stable sheaves in a sec. So that's the Gesiger situation. Now, what's important I think to take from this is that these moduli spaces are projective, but not projective with any sort of canonical polarization. They're just projective. You can embed a quote scheme in a Grassmannian, and you can do GIT, but there's no necessarily preferred polarization on these moduli spaces. On the other hand, you have Bridgeland stability. So in Bridgeland stability, again, this was discussed in Christian Martinez's talk, but here it's a stability on derived objects. So derived complexes of, let's say, vector bundles or coherent sheaves. And in order to do it, we need a slope, and we need an abelian category on which to compute the slope. So we get the abelian category A by choosing a bounded T structure on the derived category. One available bounded T structure is the standard one, for which the heart is coherent sheaves, but it turns out in all cases other than curves, that's not the T structure that you want. You want a perverse T structure on the derived category. Anyway, so you have the derived category. So we choose the T structure, and then we sort of, in some sense, refine the T structure with a slope, which is usually, again, today's theme seems to be physics. So the physicists call it a central charge, which is a linear map from the K group to C, from this gamma to C, which is basically just, a pair of linear functions that take as input Turing classes of coherent sheaves or vector bundles or complexes, and then give you real numbers. I've done this slightly differently just to keep Izet awake than normal. The way I write my slope, it's y over x. So since the slope is supposed to go from -infinity not inclusive to +infinity, my objects are mapping under Z to the right half plane. But anyway, so the idea is the objects of A are positive in a sense that they all map, that they're all required to map to the right half plane union the open right half plane union the positive y-axis, and the slope is simply the slope of the vector Z of E, or Z of the Turing character of E. So again, if we were doing vector bundles on a curve, then we would just be taking y would be the degree and x would be the rank, right? That's the usual. Right, and so what's okay? So this is the world's least. This is going to be the least precise definition of a stability condition you'll ever see. But again, Christian gave a very precise definition of a stability condition, which means I don't have to be precise. I can sort of go for this sort of intuition. So there's two ideas behind this. One is that there should be enough stable objects. basically the idea is that if I have an object that is unstable, then by definition it has a subobject of larger slope, right? And if that's unstable, then it has a subobject of larger slope. And maybe, so the idea is that we should have enough stable objects so that every time you have a chain of subobjects of larger and larger slope, it should terminate in at least a semi-stable object. And even a semi-stable object should have subobjects of the same slope, and that should always terminate in a stable object. So basically, stable objects are the building, there are enough stable objects to be the building blocks of every object in every element of A via filtrations, via finite filtrations. So there should be enough stable objects, and then stable objects should sort of stay away from the kernel of this Z. This is called the support property. So basically, you should be able to separate all the stable objects uniformly from the kernel of Z via a quadratic form on gamma, on gamma tensor R, the vector space that is negative definite on the kernel and positive semi-definite on semi-stable objects. So there are lots of plenty of stable objects, enough to assemble everything in some finite way, and they're also somehow separated from the kernel of Z. So with that pseudo definition, the theorem, Bridgeland's theorem, is that the Z map, taking the set of stable objects with a natural quasi-metric on it, given by basically the measuring how anyway, there's a pseudo metric on the space of stability conditions at a topology, such that the map Z to Hom is a local homeomorphism. This gives stab X the sort of the structure of a complex manifold. Right, so for example, in the case of surface, this stab of the surface is a complex manifold of complex dimension 2 plus the Picard rank of the surface. It's also equipped with a group of symmetries. It's basically the universal cover of GL 2R oriented. So it's got a sort of a four-dimensional real dimensional group acting on it. If you restrict yourself to stability conditions for which Z has rank 2, then this is some kind of free action. So there's a lot of structure to the stability manifold. There's an additional condition. The stability condition is called geometric. If skyscraper sheaves are stable, first of all, they belong to A, or maybe a shift of A, and they're stable and they all have the same slope. And sort of the keen thing that at least that we want to know, one really wants to know, is to understand this connected component of the stability manifold that containing the geometric stability conditions. The first question you want to know is it non-empty? For a long time, there were no known examples of projective Calabi-Yau threefolds for which this was non-empty. That's been recently fixed by Chunyi Li and others. Have found a few examples. For example, the quintic in P4 has stability conditions. Then a much harder, complicated question is understanding whether the stability manifold is, let's say, simply connected, or even better, contractible. These are open questions about even stability manifolds of K3 surfaces of higher Picard rank. Why would you be interested in this stability manifold? Let's say for a Calabi-Yau threefold, well, it's supposed to play an important role in mirror symmetry. So it has definite mirror symmetry type properties for K3 surfaces, and it should also have mirror symmetry properties for Calabi-Yau threefolds. And eventually some really smart young person, maybe in the audience here, is going to figure that out in full detail. One of the reasons that Bridgeland originally studied these was because the the action of the group of autoequivalences of one of these derived categories can be a very complicated object. And if you look at the autoequivalences, sort of the stability manifold sort of acts as an avatar for the derived category. You have an autoequivalence of the derived category, well, then it acts on the stability manifold. And if you look at autoequivalences that fix the K group, fixed cohomology, then they actually act by deck transformations. So somehow the geometry of the sort of this local homeomorphism says a lot about what kinds of autoequivalences of the derived category you have. But we're interested in moduli. So here we're going to fix a Chern class and a stability condition, which again, as I said, it's going to be first a T structure and then one of this central charge, which maps objects of A to the right half plane. There's a very general determinantal line bundle construction, I think due to Donaldson maybe, that says that basically in great generality, it says that if you have an object F, let's say, of the derived category that is orthogonal to the Chern class C for the Mukai pairing, then given any family of objects of class C, you get a line bundle on the base of the family. And moreover, because of this orthogonality, if your family consists of objects that are that are simple, that have no non-trivial automorphisms other than C star, then this line bundle actually sort of descends from the gerb to the moduli space. So this is a good thing to have. And if you think this is esoteric and weird and complicated, you should realize that this is actually critical even to constructing line bundles on the Jacobian of the curve. So this is not an esoteric thing. It's very central to moduli theory. Anyway, the point is that a stability condition actually produces, again, given a class C and a stability condition sigma, then we get such a class. We get such an orthogonal class via this sort of symplectic form applied to C and, well, this fixed C and then an arbitrary C prime, just xy minus yx. This is a form. If I think of this as a linear form on the C primes, then it is then I can sort of replace CC prime with chi of C prime. This is a linear form, so it has the form chi of C double prime C prime because the Mukai pairing is non-degenerate. And that C prime, by construction of this form, is orthogonal to C double prime and therefore defines a line bundle on moduli, a moduli of stable objects, of isomorphism classes of stable objects, which if you unpack this, and it's a great exercise to check that this is the same line bundle that Bayer and McCree used in their paper, I think in 2009. Anyway, they proved that this determinant line bundle that you get from the stability condition and a class is basically a Neff line bundle on the moduli of Bridgeland stable objects. So I'm hiding a lot of very difficult questions, but basically the idea is supposed to be that unlike the Gesiger moduli, the Bridgeland moduli are actually, they're coming equipped with a polarization, line bundle or real line bundle of positive degree on curves. So I guess by Kleinman's criterion, if we knew that this moduli in advance was projective, then we would be saying that this was actually determined an ample line bundle, an ample class. We don't yet know, as far as I know, that in general that moduli of Bridgeland stable objects are are projective. I'm kind of hoping that we will find non-projective ones, but anyway. But so it should be distinguished from the Gesiger. This actually comes with the polarization, so that leads to a wall and chamber structure, which kind of should remind you of the very first talk today a little bit. So if I have a primitive class, then a generic stability condition, either for generic stability condition, everything of class C is either stable or unstable. There's nothing in between. But for special classes, in fact, there's a codimension 1 set of walls for which there exist objects that are semi-stable and not stable. So the idea is that these walls enclose chambers. In the chambers, the moduli of stable objects are unchanged, sort of complete and unchanged as you move around in the chamber. But the determinant line bundle on this thing is moving. And as you reach a wall, you pick up semi-stable objects. And then as you cross the wall, semi-stable objects are sort of, because they're semi-stable, they fit in a short exact sequence with objects of the same slope. As you cross the wall, they're replaced by objects where the short exact sequence goes in the opposite direction. The line bundle, the determinant line bundle, as we approach the wall, becomes trivial on some curves, negative on curves as I cross the wall, except that I get a new model on the other side. And if all works out well, and it's a birational model, the one to begin with, then it's some kind of partner via some minimal model program. So this is the optimistic view of this thing. But the idea is that because these moduli come equipped with real line bundle classes, then we can track the line bundle as you move around on the stability manifold. Great. So here's an application that actually, even though it's on the art from Sohaila Feyzbakhsh, which even though it's on the archive from 2016, it got updated just a few months ago. It used to be only about surfaces. Now it's a more general fact. But an application would be the following question. Suppose I have a Mumford or Gesiger stable reflexive sheaf, and I restrict it to a divisor. Well, it's kind of known that if the divisor is sufficiently ample, then that restriction should be stable, something of that nature. But Sohaila sort of realized that has proved that you can really make this precise using stability conditions. I know there are other approaches to this, but here's an approach using stability conditions that I think is very nice. So it says, suppose I fix an ample H on X, and I look at a divisor in the linear series KH. Then the idea is that the restriction to this divisor is going to be necessarily stable if K is sufficiently large, but you can be very precise, and she is in her paper, about how big K needs to be. There's the discriminant of E comes into play, and also sort of the stability of E. Basically, it's stable, but how stable is it? What's the gap between the slope of E and the slope of a maximal sub, or the slope of a minimal quotient, minimal slope quotient comes into play. That information comes into play. But the point is that out of stability conditions, you can do this. Now, here's the idea, and then I'll say a few words. So the idea is that what you do is you take E restricted to D, and you realize that it fit, of course, E restricted to D fits in an exact sequence. E of minus D goes to E restricted to D. Great. But that could be thought of as a short exact sequence if I'm in an abelian category that contains both E and E of minus D shifted by 1. Okay, so you go searching in the stability manifold for a stability condition for which E and E of minus D shifted by 1 are stable with the same slope. They belong to A and they're stable with the same slope. Okay, so she does this, and then you say, well, okay, so there's a wall corresponding to that, and if I were to cross the wall, I'd get something else. But instead, let's sort of start moving towards a chamber where the moduli of stable objects actually corresponds to ordinary stability. And so this is what she found, was that given these inequalities, you could sort of find a path. You can't avoid the walls in your path, but E restricted to D can avoid the wall. So there will be walls between this chamber where E restricted to D fits in an exact sequence that proves its stability. But as I move towards Gesiger moduli, I can rig it so that E restricted to D continues to be stable. It's not one of the things that is affected by the walls as I move. And so eventually, this E restricted D, the stability of E restricted D over here, actually propagates all the way to a moduli space that agrees with the Gesiger moduli space, proving that E restricted D is stable. Now you could really argue, there's a lot I'm leaving out. One thing is that this argument is actually solid for surfaces where we know that stability conditions exist with these properties. You have to go to some kind of quasi-stability condition in arbitrary dimensions, which is fine. But you know, if you're intrigued by this, read her paper. I think it's a very, very interesting idea and a very, I think, surprising and powerful application of the idea of stability conditions. It's like you want E restricted to D to be stable, fine. You can find it stable for some point on the stability manifold. And then you sort of have to prove that you can wind your way back to proving that it's stable for ordinary stability of bundles by sort of seeing that it evades the walls that might screw up its stability. That's one application. Another application is a big one, which, you know, I wanted to put down here because there's a lot of really interesting work by several of the co-organizers that I wanted to give a nod to. But so let's say when the Gesiger moduli is, say, smooth and projective, and again, as before, let's suppose it corresponds to a chamber in the Bridgeland moduli space. Then the idea is that you can use the wall and chamber structure to analyze ample and movable cones of the Gesiger moduli. Wealth of applications. As one example, there's a recent paper of Izet, Jack, and Copper, I forget his first name. So which applies this idea. So finding the ample movable cones of the moduli of sheaves on Gesiger stable sheaves on the projected plane leads via stability conditions. As far as I know, that's the only way to do this. Leads to very classical questions like, what are the cohomologies of the tensor products of two very general stable vector bundles? So I found this also, this is a beautifully simply stated question, which sort of surprisingly is informed by an understanding of stability conditions and their sort of applications to understanding moduli of ordinary stable vector bundles on the projected plane. Okay. So to get to some other applications, I need to kind of pass through exceptional objects, which are kind of related to the various talks on quivers, including the last one. So an object of the derived category is exceptional if the only Halms, if all Halms, including higher degree Halms, are just the complex numbers times the identity. So line bundles are exceptional on Fano varieties, but they're not, for example, exceptional on Calabi-Yau varieties because Serre duality screws up. If Hom E to E is C times the identity, then X to D of EE will be also C times, it will be also C, right, by Serre duality. So, and then a collection of exceptional objects is called an exceptional collection if the Homs going backward are all zero, including the degree zero Homs. And it's strong if the Homs going forward are all in 1 degree. So the one natural, I knew I'd run out of time, so I'm gonna do this quickly. So one natural example of this is if you take a Fano variety of index I, then the line, then OX all through OX of I minus 1 is a strong exceptional collection. I mean, the most celebrated example of this is PN, where Bailenson wrote like a 1-page paper showing that OX through OX of N on PN is a OPN of N is a strong exceptional collection, and that sort of started got an industry started. Anyway, if you're not PN, then there's going to be a sort of a triangulated category left over when I take the orthogonal of this collection of line bundles on your Fano, and this is what's called the Kuznetsov component. So, and it's a Calabi-Yau category. This showed up in Emanuele Macri's talk already, where he took a cubic fourfold, took O of 1, O of 2, and then the orthogonal was this Kuznetsov component, which he asserted was, which he pointed out is a K3 category. So it behaves as if it were the derived category of the K3 surface. On the other hand, if it's a general cubic fourfold, then it doesn't behave like the derived category of a K3 surface in the sense that it only has the rank of the K group of the gamma is only 2, smaller than the minimal rank of an algebraic surface. So in some sense, you might say that it acts as though it's the derived category of a Kähler K3, but that's not true. It's a non-commutative deformation of the derived category of a K3 surface. So in any case, so you have this Kuznetsov component, which is some Calabi-Yau category associated to a Fano variety, and so it's very natural to ask what properties, what geometry of X can you recover from the Kuznetsov category. So in Macri's talk there's a very ambitious program that I'm a part of, that where we're hoping that maybe if when the cubic fourfold is special, that you can actually prove rationality of it via sort of Brill-Noether theory applied to the moduli of stable objects on the Kuznetsov component. It's an ambitious thing. I'm still irritated that you can't conclude that the generic one is not rational, but that's one of those embarrassments in life, right? So here's an application that I want to mention, partly because I've been involved through my graduate students, and also involved from a conference, but is a simpler application is there are five families of Fano threefolds of index 2 in Picard number 1, classified by their degree, which runs from 1 to 5. The Fano, some of them are quite familiar. The degree 5 is a linear section of the Grassmannian G25. It's a rigid Fano threefold. X4 is the complete intersection of 2 quadrics in P5. This is one that's dear to my heart. I mean, I think it was one of the first things I studied in mathematics because I didn't no idea what derived categories were when I was a graduate student, but the Kuznetsov component of this is the derived category of a hyperelliptic curve, of a genus, in this case, just genus 2 curve, I think, right? So, which you would get by, yeah, so I'll let you ponder that. Anyway, it's certainly known way back the 60s, I think, that you can actually recover the complete intersection of the quadrics from the curve, from the hyperelliptic curve. That's a classical construction. But Kuznetsov was asked a sort of a different question, a Torelli type question, which is that in these cases where which are more complicated, can you also recover the variety, the X, from its Kuznetsov component? Can you recover it itself? So there was, I think Kuznetsov himself did the cubic hypersurface in P4, but sort of the idea here is to do it via moduli. So you sort of have the Kuznetsov component. There's a result. I think it's Bayer, Macri, and maybe Stellari, or maybe Bernardara. I don't know, that allows you to put a stability condition on the Kuznetsov component, and so then you try to compute moduli. And for one particular class, you can actually recover the cubic hypersurface from the moduli. This was done in a paper that came out of a conference in Toulouse a number of years ago. And then sort of inspired by this work, my students have been studying the degree 2. Degree 2 is a double cover of P3 branched along a K3 surface, branched along a quartic K3. So they were able to recover using moduli, recover the X2 from its Kuznetsov component. And similarly, finally, X1 was recovered. Well, they've almost got it. They're close to recovering this X1 from its Kuznetsov component as well. So the moral is that I think we all need to learn Bridgeland stability conditions. There's lots of applications, just to interesting moduli problems, but also just to interesting basic questions in algebraic geometry that are being solved using this highly useful tool. So I think I'll stop there. Thank you.
All right, well, let's all thank Aaron. Do we have any questions for Aaron?
Time for a glass of wine.
All right, well, if there's no questions for Aaron, let's thank him again. And let's also, I think, take an opportunity to thank Marcos, who was, I think he was the brains behind all this. He decided we should have a session and got us all together, and it's done a lot of the work for this conference. So thank you, Marcos.
Thank you.
Thank you.